Today we're going to be starting our chapter 3, part 3 lessons. Today is lesson number 1, which is just a quick review of exponential functions and then also learning about their derivatives. So today we're going to be looking at exponential functions with the base of e. Exponential functions that don't have a base of e, you will learn about their derivatives in a couple lessons because we kind of need the logarithm derivatives in order to do those. So just a few refreshers. Equation of the form y equals a to the power of x, where a is greater than 0 is an exponential function. So if a is greater than 1, we have an increasing function. So this would be something like y equals 3 to the power of x. These have asymptotes on the x-axis. These have a y-intercept of 1 and no x-intercept. And if we wanted to find the limit as x approaches infinity, then this limit would be infinity because as we head to the right on this graph, it goes up forever. And the limit as x approaches negative infinity, or as we head to the left forever, the limit would be 0. A reminder that our domain here is all real numbers, and our range would be y is greater than 0. If we have an a value between 0 and 1, so a fractional a value where the numerator is less than the denominator, this would be something like y equals 1/2 to the power of x. These are decreasing functions, meaning as we read the graph left to right, these graphs decrease. We still have an asymptote along the x-axis. And if we look at the limit as x goes to infinity, it equals 0 because as we head right on the graph forever, the y values will approach 0. If we were to head left on the graph forever as x approaches negative infinity, our y values would increase forever, and so our limit would be infinity. Our domain here would still be all real numbers, and our range would still be bigger than 0. So we looked at in chapter 1, very briefly, we looked at a base of e. So e is a number kind of similar to pi, which is terrible for me to say it like that, but e is a constant. It equals approximately 2.71828, et cetera, et cetera. Pattern does not keep repeating. This means that if we had f of x equals e to the x, that base is greater than 1. So if we graph this, it looks like the left-hand graph from above. So if we were to graph this, it would be an increasing function, left to right. We would still have an intercept at 1. We would still have an asymptote on the x-axis. So the limits that we determined above, if a is bigger than 1, would hold. If x approaches negative infinity, e to the x approaches 0. If x approaches infinity, e to the x approaches infinity. The x-axis is still a horizontal asymptote. And our derivative of e is e. We can use definition of derivative to prove that these are true. And then there's another rule in chapter 4 that is called L'Hopital's rule. We can use this as well in conjunction with definition of a derivative if we want. But derivative of e is e. Now, chain rule does apply. So if you have another function as the exponent, you need to do the derivative of the exponent as well, which is what this second line here indicates. Okay? So if u is some function, then derivative of e to the u is e to the u times u prime. Okay, so the derivative of the e part is still e, but then the derivative of the exponent you need as well, which would be u prime. Okay, so we're just going to go through a couple examples. These can get quite gross because you can have really gross exponents. or you might need to use like product rule or quotient rule and chain rule as well. So basically in this section, you're going to start to see things that you've already seen in chapter 3, but now with E involved. So if you're finding anything that has a derivative and there's an E in there, derivative of E is E, but chain rule applies to the exponent. So we're just going to do just a couple quick examples. So if I want to find y prime, if y is e to the x squared, we need chain rule. So this is essentially e to the u, where u is x squared. That's what we have here. So y prime, the derivative of e is itself, which in this case is e to the x squared. And then we need to times this by the derivative of the exponent, which would be u prime. So the derivative of the exponent here would be 2x. You technically can leave it like this, but usually if you have e multiplied by something else like a constant, like a 2, or some variable, just an x, we would put this in front. So the preferred way of writing this would be 2x times e to the x squared. For this next one, we need product rule. You have two things multiplying. You have the root x and the e to the x. Okay. I would also choose to rewrite this before I start, and I would rewrite this as x to the 1/2 times e to the x, because I don't like dealing with that root. I'd rather deal with an exponent. So for my product rule, the derivative of the first term would be 1/2 x to the negative 1/2 times the second term plus the first term stays times the derivative of the second term. And in this case, the second term is e to the x, and the derivative of e to the x is just e to the x. Now we would need to fix this up so that we don't have negative exponents. You shouldn't be leaving negative exponents in your answer here. I'm going to rewrite this as 1 over 2 root x times e to the x plus root x times e to the x. Again, technically you could leave it here, but most of the time you're going to be expected to write this as a single term, meaning you should have a fraction here, a rational with common denominators. So if I make common denominators, the problem is the right-hand side needs the right denominator. So the right-hand term I need to multiply by 2 root x over 2 root x. When I do that, now I have e to the x over 2 root x on the left plus 2x e to the x over 2 root x on the right. And then I can write this as one fraction. Now on the top, if we want, we could factor out an e to the x. And you'd have 1 plus 2x all over 2 root x. You could also rationalize if you want, but you don't need to. So either of these would be fine. Again, if you left this in this step here, it's not incorrect, but if you have a picky professor at university, they probably won't give you marks. Okay, so really it's going to depend on how far your professor asks you to simplify this. But usually you would simplify it next time. There are two special hyperbolic functions here that you might see come up here or there. They're not used much unless you're taking physics, but if you see them, this is just so that you know what they are. So there's hyperbolic sine and hyperbolic cosine. Hyperbolic sine is equal to e to the x minus e to the negative x over 2, and hyperbolic cosine is e to the x plus e to the negative x over 2. We've been asked to show that the derivative of sine is hyperbolic sine is equal to hyperbolic cosine. So in other words, we've been asked to show that the derivative of e to the x minus e to the negative x over 2. We're trying to show that this is equal to cosine x, hyperbolic cosine x. So we want to find this derivative. So we can take this half out if we want. Okay. Once we do that, we need the derivative of e, which is e, minus the derivative of e to the negative x, which would be e to the negative x times -1, because the derivative of the exponent is needed here, and the derivative of the exponent would be -1. We can then simplify this to get e to the x plus e to the negative x, which is hyperbolic cosine if we bring that negative or that 1/2 back in. So we have shown that that's true. Okay. So again, we don't have to take that 2 out. We could leave it and just do derivative of the top minus the derivative of the other part of the top. We don't need quotient rule here because there's no actual function on the bottom. It's a constant. So you can also separate these into half e to the x minus half e to the negative x. Like you can split this into 2 separate fractions if you want and deal with it that way. I've shown way more steps than most of you would probably do for this question. But that's it for today.